Hello and welcome! Today we're going to be detectives in our own kitchens. We're tackling a delicious mystery that I'm calling the case of the rising dough. So here's our big question. How in the world does a heavy, dense little ball of dough turn into a beautifully light, airy, fluffy loaf of bread? I mean, it seems like magic, right? But it's not. It's science. And we're going to follow the clues to figure out exactly what's happening. You know, every good mystery needs a suspect. And for this case, our main suspect is a pretty common kitchen ingredient. So let's start by building a profile on our main fungus of interest, yeast. Now, if you just look at it, yeast doesn't seem like much. It's just this dry, grainy powder you get in a little packet. Honestly, it looks about as alive as a spoonful of salt or flour. But, as any good detective knows, first impressions can be really, really deceiving. This is the first, most important question we've got to answer. I mean, think about it. If yeast is just some lifeless powder, how could it possibly have such a huge effect on our dough? We need a solid, scientific way to figure out if it's actually alive. And lucky for us, scientists have a tool for this exact problem. It's a handy little checklist called MRS GREN. It's basically a list of the 7 things that all living organisms have to do to be considered, well, alive. So let's run our suspect through the test. Okay, so you've got movement, respiration, sensitivity, all the way down to nutrition. And here's the first major clue in our case. When you give yeast the right conditions, a little food, a little warmth, it does every single one of these things. It's eating, it's breathing, it's even making more of itself. It checks every single box. So, the verdict is in. Our first impression was totally wrong. Yeast isn't just some simple chemical. It's actually a living organism. A tiny, single-celled fungus that's just dormant, kind of sleeping, waiting for the right moment to wake up.
All right, so now we know our suspect is alive. The next logical step for any investigation is to see it in action. Let's move on to the next phase. We're going to activate the yeast and look for some hard evidence of what it does.
Waking it up is actually pretty simple. All we have to do is give the yeast some food, in this case sugar, and a nice, comfortable environment with some warm water. It's the perfect recipe to get it going. And after just a few minutes, there it is. You see it? Bubbles start to form. The mixture gets all frothy. This is our first piece of real, physical evidence. The yeast is efficiently awake, it's active, and it's doing something. But what are those bubbles? Those bubbles, that is the smoking gun of our investigation. It's a gas called carbon dioxide. What's happening is the yeast is literally eating the sugar, and through a process called respiration, it's releasing this gas. This gas is the key to the whole case.
Okay, so we know our yeast produces gas, but a good detective doesn't stop there. We need to know how to get the most information, or in our case, the most gas, out of our suspect. It's time to interrogate the variables and find the perfect conditions for our yeast to talk.
Now, to do this right, we have to follow a really important rule in science. We have to conduct what's called a fair test. All that means is you only change one thing, one variable at a time. That way, you know for sure that whatever result you get is because of the one thing you changed. It's how you get reliable answers.
So what could we change? Well, there are a bunch of possibilities here. We could change the water temperature, the amount of sugar, how much water we use, even the temperature of the room. For our experiment, we're going to focus on just one to keep it a fair test: water temperature.
And this shows you exactly why that's so important. Look, if you do an unfair test, like changing the water temperature and the amount of sugar, you get a result, but you have no idea which change caused it. But in a fair test, we keep everything else exactly the same and only change the water temperature. Now we can be sure the temperature is what's making the difference.
So here's our plan. We'll set up 3 identical bottles with the same amount of yeast and sugar. But for bottle 1, we'll use cold water, bottle 2, warm water, and bottle 3, hot water. Then, to catch our evidence, we'll stretch a balloon over the top of each bottle. The balloon that blows up the most tells us which temperature our yeast likes best. All right, the experiment is done and the results are in. Let's analyze the evidence and deliver the final verdict on what makes our suspect, the yeast, really perform. And wow, the results could not be clearer. The balloon on the cold water bottle barely inflated. The warm water, that balloon got pretty big. But here's the plot twist. Look at the hot water bottle. Almost nothing. What happened there? Why didn't hotter mean better?
Well, here's the crucial piece of information. Remember, yeast is a living thing. And just like most living things, it has its limits. That super hot water didn't just slow the yeast down, it actually killed it. So, our interrogation is officially over, and we've discovered that yeast has a Goldilocks zone. It needs conditions that are just right. Too cold, and it's super slow and sleepy. Too hot, and, well, it's game over. Warm is where the magic happens.
Okay, we have done it. We've profiled our suspect, we've gathered the evidence, we've interrogated the variables. It's finally time to put all the pieces together and officially crack the case of the rising dough.
So, why do we care so much about all this carbon dioxide? This is the motive. As the yeast releases all those gas bubbles, they get trapped inside the stretchy dough, forcing it to expand and rise. Those trapped bubbles are what create all the little holes and pockets inside bread, which is exactly what makes it so light and airy instead of a dense, heavy brick.
And that, right there, solves our mystery. So the next time you slice into a fresh loaf of bread, take a close look at all those little holes. They aren't just empty space. They're the fingerprints left behind by millions of tiny living fungi that worked hard to make your bread absolutely perfect. Case closed.
We've cracked one case today, but honestly, this just opens up a whole world of new questions. Why does toast turn brown? How does a sauce get thick? Your kitchen is basically a science lab full of amazing mysteries. The only question left is, what will you investigate next?